All right. Hello, everyone. You are all looking like I'm feeling today. Just a little bit tired. Just a little bit tired. Yeah. I hope that you are all actually doing okay, though, in spite of looking a little bit tired and maybe feeling a little bit tired. I would like to say that we are now halfway through this term. Yes, we are halfway through this term. Part of me is like, oh my God, we're already halfway through this term. And the other part of me is like, thank God we're halfway through this term. Yeah. We are halfway through this term. Welcome everyone back to Comp 2160 Programming Practices. I hope that you all had a good weekend. Take it you had a test today? Today, okay. Okay, I'm sorry. And then you had a test on Friday. It's just like test gauntlet right now. It's the middle of the term, and that's kind of what happens in the middle of the term. But it never feels very good. So I feel terrible for you, but let's keep trucking on. We're going to be continuing to work on this long-term example, the strings.c. We're going to be starting from what we had at the end of lecture 11. So please have that ready in your editor if you want to follow along today. By the end of today's lecture, what you should be able to do is define the implementation of an ADT with a private data structure. So I've taken off the define the interface now. We've already finished defining our interface. The interface may change over time at this point, but we're kind of finished with that part of it for now. We're going to be focusing on the implementation of the private data structure. The parts that I want to add to this private data structure are continuing to add preconditions, postconditions, and invariants, so making sure that we're adhering to design by contract. But really specifically, I want to change this to use a linked data structure in today's class. So our string right now is a string that's limited to 100 characters because that's how big the array is that we have set in our code. And so I want to switch to using a linked data structure to represent that. And then once we do that, we're going to move on to taking a look at testing. And the focus for today is about not really the mechanical aspect of like making test suites, but rather coming up with appropriate kinds of data, so representative inputs and outputs for what you would expect a functioning piece of code to produce if it were to be given a specific input. And we're going to be looking at that in two different cases. General cases, so like this is what's called happy path. This is what we would normal behavior to be for this kind of abstract data type that we're working with. And then edge cases, which is valid data, but it looks kind of strange compared to what we may have seen before. So let's keep building this up. I want to start by just quickly reviewing. It's been a few days since we've seen this, so I want to quickly review where we're at, where we left last time, and then where we're going to be going this time. So I'm just going to pop open my terminal right here. I've got strings.c implemented, or I've got strings.c in my editor right now. The main things that we were doing in the last class were adding some stuff to this in terms of dynamic memory allocation. So we've got strings.h. We added these preprocessor directives, these header guards, to make sure that we don't include this multiple times in multiple different locations. Just a quick reminder that on line 14 here, we have the private declaration of the data type to use, but we're not exposing any details about how that's actually implemented underneath. And then on the left side of my screen, I've got the private implementation of this data structure. So this is actually what the data structure looks like inside of the implementation that I've got. So our header otherwise mostly remains the same. And then what we started doing here was to start working with dynamic memory allocation. So with make string, the state that we were in was that we were calling this new function called malloc, and then main.c here. I commented this out, and I would like to confidently say that I did this on purpose with this loop where I made my machine crash. I did it on purpose. It was, yes, it was absolutely intended for me to make the machine crash in class, because I was really just beautifully trying to make a point of like, this is what happens when you don't release resources after you have acquired them. We were in a state where my machine crashed because I put in an infinite loop make string, and an infinite loop make string Well, it basically filled RAM. So I've got 24 gigs of RAM in this laptop. It filled RAM with Franklin, just over and over and over again, just full of it. And then it didn't have anything left to run processes. It didn't have anything left to run the operating system. And the machine died, and our stream just ended very suddenly. It was 100% on purpose. Yes, yes. I hope you all believe me. It was 100% on purpose. So the main thing that I wanted to get to at the end of this was to be able to start releasing the memory that we have acquired. So I'm going to go down to the bottom of my editor with strings, and I'm going to be looking at this destroy string. And the very last thing I want to do here is just add a check if s does not equal null. So I'm looking at the destroy string function in strings.c. We have this assertion. We have preconditions here. We're asserting that s does not equal null. We're passing our object to our invariant. So our preconditions here are that the thing that's being passed to me is not null, and that we have a valid string. But because we can turn these things off at runtime, so we can pass that compile time, we can pass that debug flag, we can turn those assertions off. It's still possible for someone who has the released version of my code or the compiled version of my code without assertions turned on to be able to pass null. So I still want to be able to check this so that I don't get a segmentation fault if something happens. So I still want to check if s is not equal to null here. That's the state that we were in at the end. We've got this string data structure. It's private. It's hiding implementation details. We have a create string that does dynamic memory allocation. We do have a destroy string, but we never got to the point of calling it. So let's, sorta. Let's go through the process of finishing resource management with dynamic memory allocation. Then I want to add more behavior, and this is going to be kind of a maybe. I want to leave that to the next part after I do the linked data structure, because I want to make sure that we have a linked data structure going into what we're going into next. I want to take some of the crazy design by contract stuff that we added to char at out and use const instead to make sure that we're not modifying something unintentionally in the code that we're writing. And then I want to replace arrays with linked lists in the implementation that we've got. So let's call free. Let's call this destroy string. So the expectation here, I'm going to go up to create string here, or make string. The expectation here is that whoever calls make string then has the responsibility of calling this destroy string function. They can't just call free themselves. So we can actually mechanically go through the process of calling free. I'm going to delete these comments now. I can go through the process of saying this. I could do this, free my string, but I don't know what is inside of my string. The public interface that I have from strings.h here hides what's inside of this. And when I call make string and when I call other functions on this string object, I don't know if the library internally is allocating more memory. So if it's calling malloc more times than that. Free is not recursive. It's not recursive. So it's not going to be able to say that this points at something that has been allocated dynamically, and then I should recursively call free on that. If I call free, all this does is release just the string pointer. So if I had other stuff inside of that, we're going to get to more dynamically allocated stuff inside of that. It's not going to go through the process of releasing those resources that this resource points at. So to destroy my string, I would have to actually go through the process of calling my destroy string function. So call destroy string function to have the library release all resources it has internally acquired. So I'm going to say destroy string, and I'm going to pass to it my string. I'm going to close strings.h for a second, and I'm going to open up I'm going to close strings.c, and I'm going to open up strings.h. And I'm going to go to this make string. And what I want to say here is I'm going to zoom this in. It may return null if memory cannot be allocated on the heap. And I'm going to add a little comment to this. Caller must destroy string by passing this instance to destroy string. I want to make sure that the person that's using my library knows that it's their responsibility to give it back to me to destroy later. So if you're using my string library, you must destroy this by passing it back to me and letting me destroy everything. So now I'm going to exit out of main. I'm going to write and quit. I'm going to clang -w all strings.c. I'm going to recompile my strings library. I made that change in strings.c, so I need to recompile the library first. Remember that we don't have a main function in strings.c anymore, so we're passing it this -c flag to just say compile it into code, but this isn't code that we can run as a program. So I'm going to compile that, and then I'm going to compile main.c with strings.o. So this time I'm not passing -c to say just compile it. I want you to compile main.c, and I want you to link it with this implementation strings.o, and I want you to produce this program that's called main on the other side. So right now, main doesn't do anything. It acquires resources with create string, and then it releases those resources with destroy string, and then it terminates. That's kind of the state that we're in right now. We have any questions about the state that we're in right now? Yes? It's a good question. So I'm going to open this up again, strings.c. Right now, the internal private structure of characters is that it contains an entire array and it contains a single integer. If I were to call free on that, it would work right now because everything is self-contained. It's literally an array and an integer. Very shortly, we're going to change this to be node star head. And head is going to point at another node, which points at another node, which points at another node, and so on. If we called free on just the string instance, it would just release the string. The rest of the list would just stay there hanging out, kind of being useless wasted space. But because this is an array right now, and because it's fully contained in that structure, it would work. Yeah. Yeah.
So because data isn't free either.
Can you repeat your question, please?
Yeah, because it's not like a primitive
Yeah.
characters, is the data in it not free if you just do free by string instead of destroy string?
So when we call malloc, it's giving us back just a pointer, just an address. And at that address, we will have n bytes that have been reserved for us. So so the pointer for the string now refers to an address somewhere in the heap, and there's 100 bytes of space, or 101 or 104 bytes of space that have been reserved for us at that location. So it's not really in the string pointer anymore. It's off in the heap. When we call free on that pointer, it releases that 104 bytes to be reused by something else. Yeah. Okay. So I'm going to change that back for now. Any other questions? We okay? I need to see 70 thumbs up right now. Yeah, okay, good, thank you. So, One of the things that we did that was kind of crazy overkill with char@. Char@, reminder, is this function that just goes through the process of returning an index in a string. So here's char@ in its beautiful entirety right now that has this like mega function that goes through the process of copying the entire string before we start to make sure that as a post condition, we haven't actually changed the contents of the string. If when you were watching that video, you were thinking to yourself, like, what the hell is going on? What is happening here? What is happening here? That's kind of crazy. It's because, yes, that was kind of crazy. It was more of a, let's try to demonstrate the idea of post conditions and what kinds of things you could be looking for. We can use const instead of doing all that stuff. Const is a keyword in C that is similar to final as a keyword in Java. If you have seen that keyword in Java, have you seen that keyword in Java? Yes, okay. So public static final as a named constant says you cannot change the contents of this thing. Const in C says effectively the same thing. You cannot change the contents of this thing. So I'm going to pop back over here to my strings example, and I'm going to open up strings.h. And I'm going to go to char@, and I'm going to change the declaration of this to be const string pointer. So now this is going to accept as input a string, a pointer to a string. The const keyword here says that we're forbidden by the compiler from making changes to the data structure. We can't even compile our code if we try to make changes to the data structure. So I'm going to zoom in on my definition here, my declaration of my function. The string to get the character from must not be null, must be a valid string. So I'm adding my assumptions to this, my preconditions. It returns the character at that index or the null byte if it's an invalid index. The contents of string will not be changed of my string, or I'm going to say the contents of S. I'm going to change this all to just be S now. The contents of S will not be changed. So all I've done here is I used to have this being a struct string. Now it's a string pointer. It's a const, so I'm not allowed to make changes to that string structure at runtime or at compile time. So I'm going to zoom out of this. And we're still here at char@. I'm going to change this definition. So it used to say struct string, but now I've got a string pointer that I'm taking as input. I want this to be const. I don't want to be allowed to make changes to that thing. And now I'm going to be able to delete a bunch of stuff. I'm going to be able to delete all the code that I had for copying and then asserting that the contents of the string was the same at the end. So everything here that's in if ndef ndebug, I'm going to delete. I'm going to delete this stuff here. This is checking that the string's length was the same, and it's checking that the string array was the same. I don't really care about that stuff anymore. My preconditions here are going to be that the string itself is not null. So assert s does not equal null. I'm going to say check string s. It has to be a valid string as input. I'm going to add assertions on my index because I didn't have them before, so I want to make sure I've got them. Assert that index is greater than or equal to 0, and index is less than s length. I'm going to say if string, if s does not equal null, and index is greater than or equal to 0, changing that to an arrow. I'm going to change these dots to arrows. I'm just going to leave this up for a couple seconds. Whoops, I got to change this to an arrow as well. Okay. Okay. So this looks a lot nicer to me. This looks a lot nicer to me because we don't have all this extra stuff that's copying strings and checking the contents of the strings before we get to the point of returning a single character from this string array. I want to call this. I want to make sure that it actually works before we bail out and leave it. So I'm going to zoom out of this and I'm going to go back to my main function. And I'm just going to print out printf. I'm just going to print out a single character. The character at 2 is %c. And I'm going to say char at my string 2. I'm going to open up another terminal here on the bottom. I'm going to change into that directory. I'm going to compile my strings library first. Whoops. Oh, I didn't change the names of all these things. Okay, so I'm going to zoom in on this one last time. And I'm just going to go through here and change string to just s. Okay, I'll try compiling this one more time. Passing const string. Okay, this is a fair point. So I'm going to zoom up back to my invariant, my check string. My invariant should also not change the contents of the string. So I'm going to add const to this as well. So let's zoom in on this error message here. This is a warning. It's saying you're passing a const string to some other function that doesn't have const on it. This is a fair warning, and it kind of makes sense to make sure that we don't want to pass that thing in, because that function will have the privilege of making changes to it at compile time, and we're trying to prohibit that from happening. The other warning or error here is conflicting types. Okay, so I think I missed retyping this in when I did strings.h. So let's go back down to char at. Am I in the right directory? I'm in the wrong directory. I'm in the completely wrong directory. Strings.h to lecture 12. There we go. There we go. Okay. All right. We are good. Is everyone okay with this so far? Yeah. Yes. Can you make a function return a constant? Using the const keyword? I'm not sure what that even would mean. Yeah, no, I'm trying to think about, like, I've never done that before. That's kind of what I'm saying. To put const in front of a function would kind of mean like, here's some data back, but you can't change it. And I get why you would want to do that, but I've never done that before. Yeah. So I'll leave that as an exercise for you to try. But I don't think that it makes sense to put that there. Yeah. Okay, so I've recompiled strings. I'm also going to recompile main.c. It's set, but not used. I was in the wrong directory again. Okay, main. The character at 2 is A. 0, 1, 2, FRA. Okay, this is awesome. This is like really, really lame. I know, this is super lame. It's super, super lame, but it's really awesome that we've got this infrastructure to be able to do this now. It would be a perfectly valid thought to think we could just do all this in Java and have no problems. It would be totally valid to say that, and that's totally fine. We're going to keep trucking along with C here. Okay, so I'm going to go back down to char at one last time here. Leave this up for just a second, and if you've got any questions, let me know. Cool. Okay, let's go. Let's keep going. Let's make a new implementation of this. I want to make an implementation of this that uses linked lists instead of arrays. I want to do this without having to change my main function. I have a main function here now that calls makeString, it calls char at, and it calls destroy string. I don't want to edit this code. I just want to be able to make changes to the implementation that we've got. So I'm going to quit strings.c for now. I'm going to copy strings.c to be strings array.c. I'm going to remove strings.o. And I'm going to rename strings.c to be strings list.c. So now I've got two copies of the same thing, but I'm going to start editing strings list.c. I'm going to zoom into this. Strings list.c is the place where I want to re-implement everything as a linked data structure. A linked data structure in C is a structure that has a pointer to its own type, basically. I'm going to start here by defining a new structure. And I want to make clear that I'm not editing strings.h here. We're going to keep reusing strings.h, but I am not making changes to my header file. The header file is defining the public interface for this type. How I implement my public interface is completely up to me, and I don't need to change the public interface to make changes to how it's privately implemented. I'm going to start by saying struct node. Node, I'm assuming, just quick thumbs up, yes, node is a common enough word that I don't need to define what a node is. Yes, good. Everyone knows what a node is. This is going to be a character node. This is going to be a list where what it contains is every node will be a character. Every node in the list will contain a character. I want this to be every node. Every node in the list will contain one single character. Every node in my structure needs to have the character that it's going to contain. I'm going to say character C. And it also needs to have a pointer to the next node in the list. A pointer to the next node in the list is going to be of type pointer to struct node. And I'm going to give it a name that's imaginatively next. So we start declaring a node type here. Inside, we've got a pointer to the next node, and we've got the actual data that we want to put into this node. I'm going to delete lines 18 and 19 here. My string will no longer have a maximum length. Because I'm doing this dynamically allocated list, I can have as many characters as I want, up to 24 gigabytes. So I can only put my name in here 24 gigabytes worth times. I'm going to put an instance, a reference to a node here, head. This is the head of my list. Again, we all understand what the word head means. Yes? Good. A string is now a list of characters, a linked list of characters. I'm going to start working my way down. The very first place I want to visit is my constructor function. So makeString had some preconditions that were based on that the characters that we've got in here are based on an array. I'm going to delete this precondition on line 48. We no longer have to enforce this. We don't have to have it be less than 100 characters. So I'm going to delete that. I still need to allocate with malloc the size of string to begin putting things into my string. I still need to check if my string does not equal null. I'm going to change this to be if numchars is greater than 0. And here is where we're going to have to start changing stuff. So I'm going to delete lines 68 through 70 here. And I'm going to add a new comment. Copying the string requires building a list. I'm going to say my string at head is equal to, and we're going to use that same function call, malloc. My string at head is equal to malloc size of, and then this time struct node. I would like to get enough space to put a single node into. I want to say if my string at head does not equal null, if it is returned something to me, so I have been able to successfully allocate space in the heap for this node, then what I'm going to say is my string at head, and then arrow again, C is equal to, I'm going to scroll up because I can't remember the name of this parameter, characters, is equal to characters at 0. And we're going to have to do this operation for every character that is in the string. I want to have a new node. I want to copy the character into that node, and then I want to go to the next character and do the same thing for the next thing in that string. Requires building a list. We need a loop. What kind of loop? What kind of loop should we use? We got two kinds of loops. We got a for or a while. Whoa, 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 whoa. I'm hearing for and while. Okay, let's think about this. While is an event-based loop. I want to keep looping until an event happens. For is a loop where I want to apply the same operation to everything in a sequence or an array. Take a second. And I'm going to say 1, 2, 3, and then on third beat, shout it out. Okay, so 1, 2, 3. Good, thank you, good. Yes, yes. Okay, so we want a for loop. I want to apply this same operation to every character that's in that string. So I'm going to start by doing this. For int I is equal to 0, I is less than numchars, I++. I'm going to move this stuff over. So remember to, in Vim, if you're doing this in Vim, to get everything highlighted, press V to enter visual mode, use your arrows to highlight lines, and then do greater than sign to indent everything over by 1. And then I want to put my closing brace there. I don't want to do this because it's going to keep putting my head as the last character that we've looked at. We're going to have a backward string, which is not quite what we want. That'll be OK. I'm going to leave it that way for now. I'm going to leave it that way for now. I want to say my string head is equal to malloc size of struct node. I want to say if my string head does not equal null, then set my string head to be equal to C. I need to copy something here. I got to copy something. So I'm going to go up to the top of my function, and I'm going to make a new variable, struct node next, and I'm going to set that equal to null. I'm going to delete a couple comments here just so we can see more on the screen at the same time. So I've got this next. I'm going to say next is equal to my string head. I'm going to copy the current head. I'm going to say my string head is equal to malloc. If my string head does not equal null, then I'm going to say my string head next is equal to next. So I'm going through and building up my list here. The very last thing I'm going to do is change 0 to be I. We okay with this so far? Here is my constructor function. I'm going to go through, and I'm going to move to the next function. The next function that I want to change here is going to be checkString. So I'm going to go up to my invariant. I'm going to delete the end of this assertion. All I care now is that it's greater than or equal to 0. And I'm going to write a comment here. I'm going to comment this line out for now. And I'm going to paste it right here. Before, we had exercise for the reader. Implement checking if the number of characters before the null byte is equal to length. If you do this, you should wrap this here with if, ndef, and debug. Because our string is now a list of characters instead of an array of characters, we can't just do this really quick lookup where we check to see that the last character in the string was the null byte. We're now sort of just forced to do that. We have to write this loop. We must write this loop to go through and find the nth node in the list. So thinking back to like 1010 and 1020, and then maybe really painfully thinking back to 2 hours ago or 1 hour ago when you did your 2080 test. What is the big O of search on a list? N. Where it was constant time before to go to a specific item in this list, it's no longer constant time. We are forced to do these linear things to go through and find something. So let's do it. Let's do this really quickly. In my check string function, I'm going to have a pointer to next. I'm going to start searching the list until I find either something that ends with null or either something that ends with null, so it has nothing at the end of it, or I found the null byte in the character. So I'm going to say struct node pointer cur. I'm going to set this to be equal to null. I'm going to say while cur does not equal null. So I'm going to continue to loop. I'm going to have a counter is equal to 0, while cur does not equal null, and cur point at C is not equal to the null byte. So I want to keep searching through elements that are in this list until I either get to the end of the list or until I found the null byte in the character that I'm searching for. The thing that I actually want to check here is assert that counter is equal to s length. To accomplish this one thing, I now have to do both scan through the whole list to find this, to count things and actually check that it is what it says it's going to be. So I'll say cur is equal to null. I'll actually start by saying cur is equal to s head, the head of the list. And I'm going to check here if cur next does not equal null. If the next thing is not equal to null, then counter plus plus, and next is equal to cur next. So this is iteratively scanning through my list. Iterate over the list until we get to the end of the list. We found a null pointer, or we get to the null byte in the character field of that structure. On line 47? Sorry. I don't have it defined anywhere. There. Thank you for catching that. Yeah. You know what? I'm really sorry. This is what I was trying to say. Yes, yes, I'm sorry. Thank you for straightening me out here. Yeah.
Like the dash greater than sign when the structure type that in the header file. So, but we can do that here anyway.
Yeah, so the question is, I thought that we used the arrow sign, so the dash greater than when we had a type def. The dash arrow is more about that asterisk symbol than it is about type defing something. So when we're using pointers is when we're using that pointer symbol. That it's been type defed is kind of irrelevant. We can have type deft a structure that's a stack allocated object and then use dots. It's only going to be that we're using that when we have the asterisk for a pointer. Yeah. Okay, so the question is about the difference between the dot notation and the arrow notation. So I'm just gonna have to write this down here for now and talk about it, kind of hand wave a little bit. Differences between dot and arrow. So we use dot when we're doing stack allocated structures. Whenever we've got a stack allocated structure, we will always use the dot notation. We'll always use the dot notation. We always use arrow when we're doing heap allocated structures. So this is always going to be a pointer. This will always be a pointer. The arrow notation is actually shorthand for this. So if I were to say I've got cur here, dot next, the arrow notation is shorthand for this. And the arrow notation is shorthand for here is a pointer. This thing contains a pointer. It's a variable that has an address in it. This here says dereference the pointer. Follow it to its address in memory. And then dot says find the property that's at that memory reference or that memory location. When we were doing dot here with stack allocated things, in the same way that an array is just an address in memory, a stack allocated thing is also an address in memory. So the dot there gave us like the address and then to the thing. This is going to be give me the address in memory and then dot and then get that thing. And then this arrow is shorthand for this notation. Yeah. Yeah.
I thought the ampersand gave the address.
This says follow the address that's at the pointer. The ampersand says give me the address of the thing. Yes. When I want to use the value of it. So I might want to I might want to put the address of something into a pointer, and I would use the ampersand symbol to do that. Yeah, yeah. Okay. Yes, please.
This is somewhat of it. Somewhere you didn't type it in. Would we be able to do the same flow, but not in a header block, but in it, maybe in a string?
Yeah, that's a fair question. So I'm going to go up to the top here. And the question is, can we do a type def for our node? And I'm guessing it's like, I don't want to type struct uppercase node out all the time. Yes, you can. You can say type def struct node, and then you can just use the word node here to refer to things. You still have to define the contents of the struct with struct whatever, but then you can use nodes internally if you want to. And then every other place that I've got struct node, you can use node. Okay. I'm going to go back down to check string again. I'm going to leave this here for right now. The things that we have done is that we've declared a type of node. This is our linked structure. Here, we're putting a character into this node structure. Excuse me. In C, we don't really have generics like you have in Java, so we don't have a way to quickly change the type of the contents of something. For now, when we're building up linked structures, we have to build up a linked structure that represents a linked structure for that specific type. So if I want to build an integer linked list, I need to build an integer linked list and an integer node. If I want to build a character linked list, I have to build a character node. If I want to build a string linked list, I have to build a string node. The other thing that we've done is in our makeString function, we've now started to copy the contents of the string into this list by building up a list structure. So we've got a loop here that's allocating space for a node, an instance of a node. And if we get something that's not null, so we're doing this defensive check to see if malloc is actually returned successfully, then we're inserting this list into inserting this node into the list. I'm going to add that one keyword here, insert node into the list. We're inserting that node into the list. In the check string function, then, we are iterating over the list. So I'm going to go back up here. We are iterating over that list until we get to the end of the list or we get to the null byte. I'm going to leave this here for now because I do want to talk about the assignment before we run out of time. Are there any questions about this before I switch to talking about the assignment? Yeah.
I just have a quick question on destroy. I was reading online that I've read some things that are saying it's true and some are saying it's false, but some people have been saying it's good practice to set the pointer to null after freeing it. Is that a good thing or whatever?
So the question is, I'm going to go down to destroy. I'm going to find destroy. Do you mean here? In this context, it's kind of irrelevant because once you return from this function, s is not, this copy of s isn't there anymore. It's because that pointer is a stack allocated pointer is just kind of gone. If I go back to main, so I'm going to pop over to main really quickly here. If here I say my string is equal to null, that's another place I could do it. It very clearly states to me reading this code later that that's null and I shouldn't use it anymore compared to just passing it to my string. I don't. But it seems like it could be a reasonable thing to do as an indicator or a flag to the reader to say that this thing is no longer valid and eligible to be used. Functionally, there is no difference. C, the only way that you can release resources is to call free on those resources. If you just set something to null, it's just going to leak memory in the same way that we had before. Any other questions? OK. So let's switch over to my web browser here, and let's take a look at assignment 2. So assignment 2 is, you might notice that it looks a little similar at the very top. I'm not a super imaginative person. I find it really hard to come up with novel ideas for assignments, and you can really see that sticking out here since this looks really similar to the first assignment that we had. The main difference between the first assignment and this assignment is that I'm not asking for code that does balance checking on brackets, but rather I'm looking for you to identify the matching bracket in something. So the examples here are given a bunch of inputs where we're asked to find a matching bracket. If I've got a string that looks like this one, and I'm asked to find the matching bracket for this one right here at position 1, then my code should return the position for this one, which is at position 6. This is the one that closes that bracket. This is something that you're going to be going through and building up iteratively. The first part of this is going to be building a stack. Then you're going to be testing your stack. You're going to be writing some testing code to evaluate the behavior of the stack. And then you're going to use the stack to actually implement that functionality. This is the list of learning outcomes that are being assessed on this assignment, and they are primarily related to design by contract and testing. The first part here is building a stack. This is going to be implementing an interface that has been provided to you. The interface that's been provided to you is right here. This is stack.h. That's not what I wanted at all. How do you zoom in on this app? I don't know how to zoom in on that app, so I'm going to switch over here, and I'm going to go open up stack.h. So here is stack.h. This is the stack.h that you've been provided with. This resembles the structure that we had before. So we are hiding the implementation details of this. We're only declaring the type. We've got functions here that are creating a stack structure. We've got all of the operations that you can do to a stack. And we've got a function that will give you the ability to destroy a stack after it's been used. The comments here generally describe the preconditions and postconditions for the operations that you are applying. They generally describe these preconditions and postconditions. You are not permitted to change this header file. You cannot change this header file as part of your implementation. You can have additional functions in your implementation. You're allowed to have as many functions inside your code as you want to have, but you cannot change this header file. I want to give one tiny example here that's related to this. And it's related to the peek function. The pop and the peek function are using something that's just a little bit different than what we have done before. The pop and the peek function are using output parameters to set the value of the thing that's being returned from the stack. So I have a Boolean that's being returned from this function, but I'm passing to it a pointer that I want to populate. To call this peek function, so peek is look at the top value on the stack, but don't pop it off. Don't make changes to the stack, just look at the top value. To call this function, we need to do something like this. I would declare a variable called value, and then I would say make the stack, push stuff, use the stack, however you're going to use it. And then to call peek, I would say bool, I don't know, something like peeked is equal to peek. I'm going to pass an instance of a stack into this. So S is my instance of stack. And I'm going to pass the address of, so this is related to your question here before. I'm going to pass the address of this stack allocated variable. So int value is a single integer here. There's just one single integer. I'm passing the address of, this is an ampersand, so A for ampersand, A for address of, the value variable itself. Peek inside is going to use this. Then I would be able to say something like the value I peeked is %d and then value. So that's calling this function from the outside. Inside the peek function, I can set that value that's been passed to me by dereferencing it. So to set the value in star value, I would need to dereference the address, the pointer. So inside peek, I would say value is equal to something. Set it to the value that I've taken from the top of the list. So this block of code right here is on my main function. I'll declare a stack allocated variable called value. I will pass the address of that stack allocated value to my peek function. And then inside the peek function itself, I will dereference this pointer right here. So I'll just put a star in front of it when it's on the left side of an equal sign, the name of the variable, and then just treat it like a regular variable at that point. So I can say equals, and then it will make changes to that value at that address. I'm going to leave this here for now, and I will take this out and I'll put it in another file and I'll put it beside the assignment so that you've got a copy of this. But you are not permitted to change the header file. Once you've got this header file, that's the thing that you're implementing as part of the interface for part 1. This is going to be assessed using a rubric that's similar to the first assignment. I will be able to give you back your assignments hopefully tomorrow so that you have a sense of how you've been assessed on the first assignment so you can make changes if you need to for the second assignment. I'm going to scroll down here to testing the stack. In this part of the assignment, you're going to be writing a test framework for your own code. So you will have implemented the stack. Now you're going to be writing code that will test the behavior of the stack that you've implemented. Ultimately, you're going to be writing a main function and then other functions that will call the functions on your stack. So I want to create a stack and then push something. And if I pop off of that stack, do I get the thing that I just pushed, as an example? You're going to write code to do this. You're going to write code that will implement a test suite. We're going to be looking at testing a little bit today. And then the other part of this is that I've compiled a bunch of stacks, and I've given them to you as a bunch of stack.o. But I'm really bad at programming, and I've done a bad job of most of them. And the test suite that you write, you can compile it against the stack compiled that I have compiled and provided to you. And your code should find out what's wrong with my code. So the way that this is going to work is that you're going to write a test suite that will evaluate the behavior of a stack implementation. Your code is going to find things that are wrong with my code, like, for example, and this is not one of them, but for example, create stack always returns null. So if you call create stack on my code, you link it with stack1.o and you call make stack and it always returns null, that's a bug in my code. There are 5 implementations that you've got. One of them is correct. One of them does correctly implement a stack, but the other 4 have something wrong with them. In this part of the assignment, what I'm looking for you to do is to use your test suite to identify that problem. in each of those if there is a problem, and then tell me what the problem is. So like, what's the problem that you're observing with the state of the stack that I am giving back to you after you've made changes to it with the functions that you're calling on it? The last part here is to actually implement the bracket matching code, to actually implement the algorithm. And the algorithm is straightforward once you've got a stack. When we were doing this with balanced brackets, we were using recursion as a stack. As we call functions, or as we repeatedly call methods or functions, we're just adding to a stack. And then as we're returning from them, we're popping off of that stack. We can do this iteratively with a stack. We have a stack, and we can just do this iteratively. The idea here is that if you get an input, and it has a number that refers to the first opening parenthesis that you're trying to find the match for, if you push opening parenthesis locations onto the stack here, and you pop them off as you encounter a closing parenthesis, when you get to this one here, you're going to pop off the one that matches the input value that you were given. So you push, 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 and then pop, and then push, push, and then pop, pop, pop. On that last pop, you're going to check to see what you get back. And if it's the same as 1 in this case as the input, then you found the matching parenthesis. Your code, by default, should print out the brackets that were given as inputs, and then use these little arrows or hats. This is the circumflex. I think that's what that name of that accent is the I don't know what it's called, the hat. Caret, yeah. 6, shift 6, I don't know. It's that thing. And then print spaces. So basically print one space, print a caret, and then print spaces, and then the other caret to say this is where the opening one was. If there is no match, so you run through this iterative stack algorithm, and you find that you cannot find a matching parenthesis for the one that has been noted here, then you should just print a bunch of X's underneath it to say that there's no match for this thing. Sorry, but there's no match. There's a bunch of inputs that are provided to you as examples, but I would like you to note that there is no longer a restriction on how long the string should be. So it can be up to as many characters as are in the test files. The test files are what the graders are going to be using to assess your code. It's not going to be some other secret file that we have that's being used to assess it. So it's going to be the same things. But your options here are to continue to use arrays for strings, or to switch to using something that will dynamically size the string as it's being read in. There's also no limit on the number of spaces that can be before this. And if you looked at the code that we looked at before with this stir function, there's also strchar that gives you the last instance of a character. So the approach here should be to find the last instance of a space as opposed to the first instance of a space to go through this. There's also a function here that you can call called a2i that will take a string as input, and it will give you back an actual number that represents that string. There is a bonus for this part of the assignment, and the bonus is to do colored bracket matching. So ignore the input number that you get, and this is as an addition to the actual implementation of this code. Ignore the number that you're given and then just print out colors to represent matching brackets. So I want to demonstrate that because I don't know, I'm kind of like, I feel kind of proud of it. I don't know, I'm really happy that it works. So I've got a program here that's called colors that implements this using a stack, and I'm going to print out the outputs for the data files that I've given to you. So as output for the happy.txt, this is what the output should be for colored bracket matching. So the ones on the very outside are red, and then the one where we've got one here, this one is green and green, and then yellow, yellow, blue, blue, purple, purple. That's the first test case. This is the second test case. These are all bad cases but I'm ignoring the input number. So I just start trying to match up brackets with colors. And if I can, I will print out matching brackets with colors. If I can't, I just don't print out the matching bracket. So in this case, I have a bunch of opening colors, but the only one that I've got that matches is that purple one. Same thing with the blue one here. These ones are all uncolored because they don't have a color going in, so they don't have a match to start with. And then we've got a sad face at the bottom that is just happily also red. These ones are very long inputs, and it's impossible to see what a single line looks like, but you can kind of get the sense of these brackets that are matching here. Here is a little bit of code. So here are some C, Java, and JavaScript code samples, and then a Lisp code sample at the top. And then the last one I've got here is fine art. And here's the inputs that we were given before, but with colors attached to them. Handing this in is going to be the same as you've got with the previous assignment. So you're submitting a README file that has a description of the code that you've written. It's also going to have the answers that you are providing for part 2 of question 2. In part 2 of question 2, I'm not asking you to provide code for this. The code that you're providing for part 2 is part 1. And then what I'm looking for here is just the list of explanations of what these things, what's wrong with each of these stack implementations that you've got. And then you're using Handin to submit the work that you've got for this assignment. Yeah. Can you repeat that, please? Yes. So in the README, so if you have a folder that looks like this one, where you've got a readme.md file, the explanations should just be in that README file. So you don't have to have an extra set of files that represent that. I would suggest that you just leave it all in the README to make it easier for the graders to see what you're doing rather than having 5 different text files that are attached to it. Yeah.
So what's most implemented in this data structure for?
Yes.
Just wanted to understand like what are going to be like our variables, or maybe what are we going to define apart from the node instant and other things in our node structure. Like characters, or is it going to be an array of whatever?
So the thing that you should be putting into your stack are integers. So this will be a stack that has a linked list of integers, where the integers are going to be used in this implementation here. So as you're, like I said, as you're going through this, it's that one. As you're going through this and you're building up your stack, the approach is basically start function, make a new stack, push 0, push 1, push 2, pop. When I pop this off, it's going to be 2, so it doesn't match 1 as an input. Push 4, pop. When I pop, it's not 1, so it's not the match. And then pop. When I pop off for this one, it's 1. It was the one that matched this one. So the stack that you've got and the interface that's defined in the .h file is all about pushing and popping integers. So your list should also have an integer type that's inside of it. So it's minimally going to be head is the top of the stack. The node is going to be next, and the value is going to be an integer. Any other questions? I will make sure there's time for questions on Thursday's class, on Wednesday's class. I will make sure there's time for questions on Wednesday's class if you have questions about the assignment after you've had a little bit of time to start working on it. I want to be respectful of your time, and we are at the end of our time. So I'm going to switch over here to today. At this point, you should be able to define the implementation of an abstract data type with a private data structure. You should be able to use preconditions, postconditions, and invariants. You should be able to define them, and you should be able to use them in code. We started this, use a linked data structure, implement a linked data structure. And then the part that we didn't get to today was create general case and edge case test data for an ADT. We'll finish up with the linked data structure first thing tomorrow, and then we're going to switch topics to looking at testing after that. Okay? Thanks all for coming, and I will see you tomorrow. Bye, everyone.